Right, so we're still in the section about matrices. And this is a quick catch-up lecture for the people who have missed the lecture because of the election. So we've seen a new definition, or we're seeing it right now since you've missed the lecture, and it's the definition for a linear combination of matrices. So what's that? We start off with a bunch of matrices and we see they're all of the same size, and that's because we're wanting to add them in a minute. And you should remember that we can only add matrices if they are of the same size. So I'm starting with a number of matrices. I've got R of them, and also with a certain number of scalars. So all the C's are just real numbers or scalars, and I also have R of them. 1, 2, 3, sorry, 4, 5, R. So I've got R scalars and R matrices, and then I'm writing an expression of this form. A scalar times a matrix plus a scalar times another matrix, and so on. That's called a linear combination of the given matrices. And the scalars, in this case, are called coefficients. It should remind you of another kind of linear something. This word is coming up very often in this course. We've seen linear equations, if you remember. It was something like 3x plus 4y, blah, blah, blah. And we'd said that they're linear because there's no such thing as x squared or xy or x to the third. There's only x and y's first order, right? And this is kind of similar. I haven't got anything like that. You know, we don't even know if it's defined, but in any case, we don't care because there's no multiplication of matrices in a linear combination. It's just adding matrices, possibly with a coefficient. Well, there's always a coefficient, but it might be 1. Okay, so this is what a linear combination is. And we'll use this definition to look at this theorem. Okay. So I've started off with A, a certain matrix. It's m by n. And then I also have a vector. And it's n by 1 vector. That's a 1. It's a funny font. Let me write it out. So n by 1, it's a column vector. And I say, well, I can write down the product. Well, yes, you can. M by n. And if you multiply this by n times 1, it should give you another column vector. It should be m times 1. You should go back and look at the definition of multiplication of matrices if that's not too clear to you. Okay, so let's say I have a certain matrix, I have a certain column vector, I multiply them together, and I get, well, presumably a matrix. It's going to be a m by 1. So I said that this thing, this new vector, it can be expressed as a linear combination, we've just seen what it is, of the column vectors of A. Okay, so I will need to define column vectors of A, or at least we've defined them earlier, but I'll need to write them down. And then the coefficients in this linear combination will be the entries of X. Okay, I'll let you show it in your spare time, but what we'll do instead is we'll try with a simple example. So we're needing to write down a certain product AX, so we need to write down a matrix and a vector. So I've taken a 2 by 2 matrix, so it's a 2 by 1 vector. A and X are here, and I've written the entries here. So they're scalars. I don't know what they are. Real numbers inside of A and real numbers inside of X. These are not variables. They're real numbers. I just don't know what they are. And I've also defined the vector columns of A. Vector columns? Column vectors, yeah. This, oops, that was funny. This is vector F, and this is vector G. F and G, they're defined here. That's a column vector, that's a column vector, and F obviously is this column, and G is this column. I'm just defining them because later on I will need this. Okay, so it said that AX can be expressed as something. So let me first see what AX is. It's just a multiplication, there's nothing special here. A times x. By now you probably know, but let me still write it down. Ax plus by, that's my first term. Cx plus dy, that's your second term. So indeed you get a 2 by 1 vector. So this 2 by 1 vector, it says that I can write down as a linear combination of the column vectors of A. Lucky I've defined them. So let's see if I can write this thing here as a linear combination of these two guys. Okay, well let me try and write down a linear combination of f and g. So I don't know what it's going to be, but it looks like this. A linear combination of f and g is what? Well, let's call this linear combination L. It's a vector. C1, certain coefficient, times the first vector, plus C2 times the second vector. We've just seen definition, so that's what a linear combination is. Okay, well, let me do the operations. I know how to multiply a scalar by a matrix, so I just did that, and then I know how to add these two things, because we've seen how to add matrices, so here we are. So that's the linear combination, and that's AX. So I said, well, if the linear combination is equal to AX, because that's what the statement says, is it possible that these two guys are equal? Well, yes, it is, of course. If what X is equal to C1, yeah, as you can see, it works. And then if Y is equal to C2. Yeah, so this can be true if C1 is X, C2 is Y. And that's what it says, didn't it? Let's have a look back. AX would be a linear combination of the column vectors of A, that's true. And then the actual coefficients, the CY, C1 and C2, will be the entries of X. That's what we've just shown. Yeah? So this shows, but that's only for a 2 by 2 matrix. So you might be able to see how you could write down a general matrix and a general vector and redo this proof. I think you could do that. That shows in a sort of very specific case. But if you want, you can try and show it in the general case. Oh, that was nice.